Every LLM, ChatGPT, Claude, Llama, does the same thing at its core. It reads what's been written so far and guesses the single most likely next word. Then it adds that word and guesses again and again. That's how paragraph gets written, one word at a time. But guessing the next word involves an insane amount of math. Your sentence gets chopped into pieces. Each piece becomes a list of 768 numbers in our case. These numbers get multiplied by millions of learned weights, and out comes a probability for every word the model knows. This tool runs GPT-2, a real transformer with 117 million parameters. Everything you are about to see is real data, not a simulation. Let's step through it.
Keep houseofthings.com open in another tab. You will want to play with this as we go along. Please find the link in description.
I have typed to be or not to. Now, this is the raw text. The model can't do math on letters. It needs to convert this into numbers first. First, the text gets split into tokens, not words, tokens. Sometimes a full word, sometimes just a fragment. Each one gets an ID number from the vocabulary of 50,000 possible tokens in our case. Now, here's where it gets interesting. Each token gets looked up in a giant table and turned into 768 numbers. It's embedded or its position in a higher dimensional space. These are actual numbers. Each row is one token from my prompt. 768 columns of numbers that encode that token's meaning. We are only showing the first 32 here, but there are 768 in total. This can go up to millions in large models that you use daily. But meaning alone isn't enough. The model also needs to know word order. Dog bites man and man bites dog have the same words but completely different meanings. So there's a second set of numbers, position embeddings, that encode where each token sits in sentence. Position 0, position 1, position 2. Add them together and you get the combined embedding. Meaning plus position. This is what actually enters the transformer. And here's what these combined embeddings look like when you project them into 2D. Each dot represents a token from my prompt and the nearest neighbors in the vocabulary space with similar embeddings. At this point, every token is independent, doesn't know what B means. They are just isolated list of numbers. The next step is where they start talking to each other. This is the core of the transformer, self-attention. Every token needs to figure out which other tokens matter to it. Here's how it works. Remember that combined embedding, the list of 768 numbers from each token. For each token, it gets multiplied by 3 different weight matrices. The first multiplication gives you the query. Think of it as token asking, what am I looking for? See, this on the left is the token embedding. It's 768 numbers in the middle. In the middle is WQ, a matrix of learned weights. Multiply them together and you get Q, the query vector. These W matrices aren't computed on the fly. They were learned during training on billions of words. They're frozen now. That's where the pre-trained in GPT comes from. The same WQ is multiplied for every single token. The second multiplication gives you the key. That's the token saying, here's what I contain. The third gives you the value. Here's the information I'll pass along if you need me. Every token now has a query, a key, and a value, all from the same embedding, just multiplied by different weights. Let me click on different tokens, see how embedding on the left changes, but W matrices in the middle stay the same. Same weights, different input, different output. That's the whole trick. This grid is the result. Each cell is the dot product query of one token times key of another. Higher number means more relevant. But notice something, the bottom right triangle is always all negative infinity. That's the casual mask. GPT-2 can only look backward. Each token can attend to itself and earlier tokens, but not future ones. That's what makes it a language model. It can't cheat by looking ahead. These scores get turned into percentages through softmax, and those percentages decide how much of each token's value gets mixed into the result. That entire attention process, query, key, value, scores, mixing, happens not once, but 12 times. Each cycle of those 12 times is a layer. Think of each layer as another pass of understanding. Each one refines what previous one produced. Watch, here's the input to layer 1. It's the combined embedding we built earlier, and here's the input to layer 1. It's the combined embedding we built earlier, and here's the output. The numbers change. Click on layer 6, different input, different output. Layer 12, by now the numbers look completely different from where they started. Each layer has its own set of weight matrices, its own QKV, and look, each layer has 12 attention heads, each one learning to focus on different relationships. Some heads focus on the previous word, some focus on the first word, some learn grammar patterns, all running in parallel. And that's what happens at every layer. 12 layers times 12 heads, 144 different attention patterns processing your text. By the time final layer is reached, each token's numbers encode the full context of the entire sentence. My model is ready to make its prediction. Look, B is at 95.8%. Have is at 0.4%. It learned this from seeing to be or not to be thousands of times during training. In a real conversation, we would add B to the prompt and run this entire pipeline again. Tokens, embeddings, attention, 12 layers, prediction, all over again for the next word and again and again. That's how paragraphs get written. Let me try something that it has not memorized. Opposite of hot is cold. So that's the full pipeline. Text becomes tokens, tokens become 768 number embeddings. Those embeddings get multiplied by learned weight matrices to produce queries, keys, and values. Attention scores decide which tokens matter to which. 12 layers refine the result and outcomes of probability for every possible next word. All of this happens hundreds of times per response in seconds. But here's the question: how did the model learn all those weight matrices? They started as random noise. Something had to shape millions of random numbers into useful patterns we just saw. That's training. And in the next video, you can actually watch it happen in the real time. I'm going to include the link to the website in the bio. Use the tool for yourself.